In this video, we are going to learn how horizontal forces acting on the bridge deck are distributed to the substructure part of the bridge. The drawing used for our discussion today is a three-span concrete bridge. Each span of 28.8 meters is supported on a set of elastomeric bearings. The abutment and piers are made of concrete and are supported by two rows of pile driven vertically to a depth of around 30 meters. Each substructure may have different horizontal stiffness depending on the dimension of the bearings, the height and the dimension of the abutments or columns or piers, and lastly the depth and the size as well as the numbers of pile for each particular pile groups. The abutment stiffness needs to be calculated using the following steps. The first step is to calculate the stiffness of the pile group supporting the abutment. The next step is to calculate the concrete abutment stiffness. We then use the stiffness value we have obtained for the pile group as well as the column stiffness to get the compound stiffness as shown in this formula. For this exercise, we obtain the abutment stiffness to be 124.6 kilonewton per. Similarly, we need to calculate the compound stiffness of the pier using the same steps like we did for the abutment. First, we have to calculate the pile group stiffness. Here we have the value of the pile stiffness to be 7.12 kilonewton per millimeter. Next, we calculate the pier stiffness, and based on this calculation, we have the pier or column stiffness to be 70.75 kilonewton per millimeter. Based on the above values, we can use the formula to calculate the compound stiffness of the pier. For this calculation, we have obtained the pier stiffness to be 6.471 kilonewton. The pile group horizontal stiffness is determined using a software that can analyze a three-dimensional pile group system. In this example, a horizontal force of 1 kilonewton will produce a horizontal deflection of 0.0008 meter, and the output is shown here, z of 0.008 meters. When the force of 1 kilonewton is applied together with a small moment of 1.8 kilonewton meter due to the height of the abutment above the pile group. The pile coordinates are shown here, and the pile are slightly inclined. The distribution of the horizontal force is very much dependent on the type of fixity placed on each of the bearing. In this example, all the bearings are free except for one bearing in pier 1 where the bearings are fixed to the decks. This is defined as Fx. The free bearings are defined as Fr. The value of the bearing stiffness are shown here in this row. The pier abutment A1 has a bearing of 23.6. Pier P1 has a bearing stiffness of 60,480. Pier P2 having bearing stiffness of 47.3, and abutment A2 has a bearing stiffness of 23.6. The pier stiffness for the abutments are shown in the next row: 1 to 4.8, 6.5, 6.1, and 83.7. Based on the bearing stiffness and pier stiffness, we can now calculate the compound stiffness of all the abutments and the piers. This row shows the compound stiffness of the abutments as A1 as 18.8, P1 6.5, P2 5.4, and A2 as 18.4. If we sum up all the bearing stiffness, we'll get the total of 49.1 kilonewton per millimeter. Using these values, we can then calculate the distribution of horizontal force. For example, to get the force that is acting on abutment A1, the total force applied 475 is multiplied by the stiffness of the abutment A1 divided by the total sum of the stiffness, and you can get a value of 181 kilonewton. We can do the same thing for the P1. You multiply 475 by 6.5 and divide by the total stiffness of 49.1. You can get the force applied to P1 as 62.8 kilonewton. You can do the same calculation to get force transferred to